This is a very brief overview of how RC filters work. So obviously RC filters contain a resistor and a capacitor. That's what the R and the C stand for. So let's just have a little bit of an overview of capacitors. Firstly, the symbol for a capacitor is like this. And a capacitor consists of usually two metal plates separated by a dielectric or an insulator. Usually those metal plates are curled around to save space. That's why your capacitors, when you look at them, are cylindrical. Now if you have one of those in a circuit, so I attach a battery or a cell, so this is my plus and my minus. So now you've got this capacitor in the circuit, and what happens is the electrons from here, they move around this way because they are attracted by the positive terminal of the battery. So your negative electrons move around this way, and because you have a dielectric or an insulator in between these two metal plates of the capacitor, the electrons build up on this side of the capacitor, and as they do so, they start to repel the other electrons that are coming from the battery until all current stops flowing. So you have a buildup of negative charges here, and you have a buildup of positive charges here. So until no current flows anymore. So if this was a 5-volt battery, then you are left with the same potential difference of 5 volts across the two plates of the capacitor, and no current charges, no current flows anymore because the capacitor is fully charged, we say. So this takes a finite amount of time. So if I were to plot charge built up on the capacitor versus time, it builds up like this. And then if I were to disconnect this battery now, so I take it away from the circuit, then eventually this charge will leak away from the capacitor, and this has this relationship here, this exponential relationship. So you can see that the charge will also reduce with time. So this takes a finite time, and it's the fact that you have a finite amount of time that makes a capacitor have quite interesting properties for filters. So we've talked about where you have a capacitor and you have it connected to a DC supply. So here we had a battery, or you could have a power pack. Well, when it becomes really interesting is when it is charged, or when it's connected by an AC supply. So when you have an AC supply, you could either have a high frequency or you can have a low frequency. So at the moment we're not worried about the amplitude itself, just the frequency. So high frequency means that the period in between the oscillations is very small, like this. So this could be a high frequency signal coming in, and a low frequency would then have a long wavelength. So the frequency is inversely proportional to the wavelength, don't forget. So what you have when you have an alternating supply attached to the capacitor is when you have a very high frequency, then the capacitor doesn't have time to fully charge up and stop conducting. So if you were to have, here's your AC signal, and you have it over a capacitor. Just as an example, you wouldn't have a circuit like this, of course. But if you had a high frequency going through, it's as though there's not a capacitor there at all, because the charge changes direction so quickly in a high frequency circuit that the capacitor doesn't have time to react, essentially. So it continues to allow current to flow in between its terminals. So it would essentially act like a short circuit. Okay, when you have a low frequency, it's like you have a DC supply that is changing polarity, and it's changing polarity really slowly. So if it's low frequency, then it's like you're starting like this. So you have time for negative charges to build and positive charges to build, and then you switch the polarity of your supply, and the opposite happens. So you get positive charges here and you get negative charges there. So when you have a low frequency signal, then the capacitor has time to charge up, and it will start to resist the flow of current. So you can see that the capacitor resists flow of current at lower frequency. Okay, so this resistance to flow for a capacitor is known as the reactance, and it's given this symbol here. And because I've just said it changes per frequency, so when we've talked about resistors, for instance, in the past, a resistor has the same resistance regardless of what the frequency of the signal is that you put into it. Whereas in a capacitor, you see that the reactance decreases with frequency in hertz. And it has this sort of relationship here. Okay, so what does that mean when we have RC circuits? Well, you've covered potential dividers. So if I were to draw a couple of resistors in series with each other. Okay, so this is your circuit, for instance. So you have R1 and R2, and here you have some sort of supply. So let's say a 10 volt supply. So you're going to get current flowing in this circuit. Now, hopefully you already know that if your resistances here are the same, so whatever the voltage in this circuit will be divided across these two resistors. If the two resistances are equal, then the voltage is divided equally across these two. So if I measured across here, I would then get 5 volts, and if I measured across here and here, I would have 5 volts. So that's how a normal voltage divider works. You know that V is equal to IR from Ohm's law, and we're talking about ohmic resistors. So if R1 were to increase significantly, so this becomes really, really big, then the majority of the voltage will be dropped across here instead of across there. Okay, because R is proportional to V, or V is proportional to R. Okay, so that's what we have in the case of resistors. So what happens when we have a resistor now in combination with a capacitor? So this is what we're calling an RC circuit. We have a resistor and a capacitor. So this time I'm interested in having an AC signal going in, and I have a resistor, the resistance never changes with frequency, and I have a capacitor here. Okay, so now let's think about what happens to the capacitor. So the capacitor has a sort of resistance which is known as the reactance. Okay, so if we have now a high frequency signal, then when the frequency is high, then what happens to the capacitor? Well, the change in direction of the current going through the circuit happens so quickly that the capacitor doesn't really have time to charge up. So in effect, it doesn't have an influence in the circuit. The current flows both ways and keeps changing direction so fast that this doesn't react. So it acts like a short circuit, i.e. the capacitor has zero resistance. So in that case, if you were to take this circuit and you decided you wanted to use the voltage across the resistor as an output. So here we have two output terminals, and here we could use this, the V out over the resistor, to supply another circuit. Okay, so this would have a load attached to it. So if we looked at V out, if the capacitor resistance is 0 at high frequencies, then that means that all of the voltage from here will be dropped across this resistor. So V out would be very, very big at high frequencies. So if this is the way that we connect our RC filter, this RC circuit, and we use the output terminals across the resistor, then we have big V at high F. So that means we must have a high pass filter, because we're allowing high frequencies to give us a voltage out here. So the signal that we measure high voltage. So if your signal looks like this coming from the generator, it will look exactly the same out here, because if you were to measure across here, you would get nothing. So when you look at RC circuits, it's important to remember that the RC circuits always look the same. So you might see them drawn like this. Okay, so there's your resistor, there's your capacitor, or you might see them being drawn like this. And it is not the order of these that is important, it's where you tap your voltage off from. So in the previous example, I took the voltage across the resistor. So I said that between here and here is V out. This is a high pass filter, because when the signal here is very high, this acts as zero resistance, so you get all of this signal out here. If I put a low frequency signal into here, then all of a sudden the resistance here becomes large. So it's the same as having two resistors in series in a voltage divider. So if the resistance of the capacitor, I should call it the reactance, becomes really, really large, then the voltage will be dropped across here instead of here. So when you measure V out, it's going to be very, very small. So at low frequencies, V out is approximately 0. And this is why it's called a high pass filter, because when you have a high frequency into the circuit, then you get a voltage out, and when you have low frequency going in, then your voltage out will be very, very small, so the amplitude will be attenuated. Now this circuit is exactly the same as this one, the order doesn't matter, but if you tap your V out over the capacitor instead, then you will see the reverse will happen. So when you have a high frequency signal going in, then this acts like a short circuit. So this is going to be approximately 0 when you have high F. When you have a low frequency, so this is a slow wave coming out, then this has time to charge up, so it acts like a massive resistor. So at low frequencies, V out is going to be large. So low frequencies is large, so this is known as a low pass filter. And that's what the difference is between them.